The integral. Partitions and Riemann sums. We begin here with a few definitions to establish terminology. An augmented partition, P sub n, of the closed interval AB consists of a collection of n plus 1 numbers, x0, x1 through xn, where x0 equals A, xn equals B, and x0 is less than x1, is less than x2, and so on. Notice that this collection of numbers divides the interval AB into n subintervals. An augmented partition also includes a set of n evaluation points, x hat 1, x hat 2, and so on up to x hat n, where x hat sub I is between xi minus 1 and xi. Let delta x sub I equal xi minus xi minus 1. This is the width of the ith subinterval defined by our points x0 through xn. The number whose symbol is P sub n, enclosed by double absolute value bars, is defined to be the maximum of these subinterval widths, and this number is called the norm of the partition P sub n. Now let's let f be a function defined on AB. The Riemann sum of f corresponding to P sub n is the sum from I equals 1 to n of f of x hat sub I times delta xi. This is a sum associated with the function f and the partition P sub n, so we use the notation capital S of f and P sub n. Now let's look at a picture to illustrate the idea. Here's a continuous function on a closed interval AB. Here's a collection of numbers x0 through xn, and here's a collection of evaluation points x hat 1 through x hat n. Each term in the Riemann sum is the signed area of a rectangle obtained by evaluating the function at one of the evaluation points and multiplying by the corresponding subinterval width. Notice that a positive value of f of x hat sub I contributes a positive term to the sum, and likewise a negative value of f of x hat sub I contributes a negative term to the sum. So in general, we should expect the Riemann sum to contain both positive and negative terms. We're now ready to define the integral. Let f be a bounded function on the interval AB. By this we mean that the values of f lie between two fixed numbers. In other words, its graph lies between two horizontal lines. And let P1, P2, P3, and so on be a sequence of augmented partitions for which the norm of P sub n approaches 0 as n goes to infinity. This means as we add more and more points to our partitions, the maximum distance between points approaches 0. The definite integral of f over the interval AB, or the integral of f from A to B, is defined as the limit as n goes to infinity of the Riemann sum of f corresponding to P sub n. That is, the limit as n goes to infinity of the sum from I equals 1 to n of f of x hat sub I times delta xi. And here's our symbol for the integral of f over AB. This is typically read as the integral from A to B of f of x dx, or simply the integral from A to B of f. Since there are many ways that our partitions could be constructed, we need to be careful about what we mean by the right side of this definition. The limit is understood to exist if and only if its value is independent of the choice of the P sub n's. So in particular, if there are different sequences of partitions that produce different limits, then the integral doesn't exist. If the value of the limit is independent of the choice of the Pn's, then we say that f is integrable on the interval AB. If f is integrable on AB, then the integral from A to B of f of x dx can be expressed as the limit of Riemann sums corresponding to any sequence of augmented partitions, provided that the norm of the partitions approaches 0 as n goes to infinity. In particular, we can say that the integral from A to B of f of x dx is equal to the limit as n goes to infinity of right endpoint approximations using a uniform grid. We'll now state an important theorem. If f is continuous on the closed interval AB, then f is integrable on the interval AB. There are in fact many other integrable functions on AB other than continuous ones. However, this is a large and important class of integrable functions. Here we have a continuous positive function on the interval 0 to 1. Each picture shows two rectangles, the sum of whose areas is a Riemann sum with two terms, and each picture is the first frame of an animation that illustrates a sequence of Riemann sums with ever-increasing numbers of terms. Notice that as the number of rectangles becomes larger and larger, the two sequences of Riemann sums agree to more and more decimal places. The final frames of these animations correspond to about 400 rectangles each, and both of the corresponding Riemann sums are good approximations to the area under the curve. In general, if f is a continuous function on an interval AB, and if f of x is greater than or equal to 0 for all x in the interval AB, and if f of x is greater than 0 for some x in AB, that is, if f of x is not always 0, then the integral from a to b of f of x dx is positive, and it equals the area of the region bounded by the graph of f and the x-axis between x equals a and x equals b. Here we have a continuous function on the interval 0, 1, whose values are always less than or equal to 0. Again, each picture is the first frame of an animation that illustrates a sequence of Riemann sums with ever-increasing numbers of terms. As the number of rectangles becomes larger and larger, the two sequences of Riemann sums agree to more and more decimal places, and the final frames of the animation correspond to about 400 rectangles each. Notice that here the Riemann sums are approaching a negative number, and so the integral is not the area of any region. However, the integral is the negative of the area between the curve and the x-axis. In general, if f is a continuous function on an interval AB, and if f of x is less than or equal to 0 for all x in AB, and if f of x is negative for some x in AB, then the integral from a to b of f of x dx is a negative number, and minus the integral from a to b of f of x, which is a positive number, equals the area of the region bounded by the graph of f and the x-axis between x equals a and x equals b. Here we have a continuous function on the interval 0, 1, whose values are sometimes positive and sometimes negative. Again, as the number of rectangles becomes larger and larger, the two sequences of Riemann sums agree to more and more decimal places. Notice here that Riemann sums have both positive and negative terms. The sums of their positive terms are approaching the area under the graph and above the x-axis, while the sums of their negative terms are approaching the negative of the area above the graph and under the x-axis. So each Riemann sum is an approximation to the difference between the area above the x-axis and the area below the x-axis, which here ends up being a negative number because there's more area below the x-axis than there is above the x-axis. In general, the integral from a to b of f of x dx equals the difference between the area under the graph of f above the x-axis and the area above the graph of f below the x-axis between x equals a and x equals b. This is the signed or net area of the region bounded by the graph of f and the x-axis between x equals a and x equals b. So in general, the integral gives us a signed area. Example. Let's let f of x equal 1 if x is less than 0, 1 minus x if x is between 0 and 2, and x minus 3 if x is greater than or equal to 2. We'd like to find the integral from minus 2 to 5 of f of x dx. Let's first graph the function. Notice that for x less than 0, we have the horizontal line at y equals 1. When x is between 0 and 2, we have a line with y-intercept 1, x-intercept 1, and slope of minus 1. And for x greater than 2, we have a line with x-intercept 3 and slope 1. The integral of this function from minus 2 to 5 will be the signed area of the region bounded by the graph and the x-axis between minus 2 and 5. The part of that region between minus 2 and 0 is simply a rectangle with width 2 and height 1. Since that's above the x-axis, that will contribute a positive 2 to the integral. Between x equals 0 and x equals 1, the graph is still above the x-axis, and the corresponding part of the region is a simple triangle with width 1 and height 1, and so it has an area of 1/2, and so that contributes 1/2 to our integral. Between 1 and 3, the function is negative, and the corresponding region is again a simple triangle with width 2 and height 1. Its area is therefore 1/2 of 1 times 2, or 1, but since it lies below the x-axis, that contributes a negative 1 to the integral. Then between 3 and 5, we have another triangle that's above the x-axis. It has width 2 and height 2, and therefore its area is 1/2 of 2 times 2, or 2. So the integral of our function from -2 to 5 will be 2 plus 1/2 minus 1 plus 2, or 7/2. Now let's look at another similar example. Let f of x equal minus x if x is less than 1, and minus 1 if x is greater than or equal to 1. Let's find the integral from -3 to 5 of f. Here's the graph of the function. Again, the integral will be the signed area of the region bounded by the graph and the x-axis between -3 and 5. Between -3 and 0, that region consists of a triangle with width 3 and height 3, and so therefore its area is 1/2 of 3 times 3, or 9/2. Between 0 and 1, we have another triangle beneath the x-axis. Its area is 1/2, and so that contributes a -1/2 to the integral. Between 1 and 5, we have a rectangle with height 1 and width 4, so the area is 4, and this contributes a -4 to the integral. So the integral from -3 to 5 of f of x dx is the signed area, which is 9/2 minus 1/2 minus 4, which equals 0. The integral is 0 here because we have equal amounts of area above and below the x-axis. Example. Let's find the limit as n goes to infinity of the sum from I equals 1 to n of the square root of n squared minus I squared divided by n squared. Our approach here will be to try to interpret this limit as an area. Let's begin by looking at a few numbers to get a better feeling for what we're looking for. Let's make a table. In the first column we'll put n, and in the second column the corresponding value of the sum. We'll go ahead and list a few of these values. When n is 2, there's only one non-zero term, and it's the square root of 3 over 4. When n is 3, it's the square root of 8 plus the square root of 5 over 9. And then when n is 4, we have root 15 plus root 12 plus root 7 over 16. Notice that the 15 under the radical in the first term in the numerator is the value of n squared minus I squared for n equal to 4 and I equal to 1. In other words, it's 4 squared minus 1 squared. The 12 under the radical in the second term is 4 squared minus 2 squared. The 7 under the radical in the third term is 4 squared minus 3 squared. This number turns out to be about 0.624. Let's go ahead to n equals 10. Here's that sum. This number turns out to be about 0.726. Jumping forward to n equal to 100, we have this sum, whose value turns out to be about 0.780. So it appears that as n gets larger, these sums are approaching some number near 0.8. Now, let's look at our sum. We'll rewrite the summand, the square root of n squared minus I squared over n squared, as the square root of n squared minus I squared over n squared, all underneath the radical, times 1 over n. The quantity under the radical can be rewritten as 1 minus the square of I divided by n. Now the numbers I divided by n as I goes from 1 to n are simply the right-hand endpoints of subintervals of width 1 over n between 0 and 1. So what we're actually looking at here can be thought of as a right endpoint approximation to an integral. In fact, the integral of the function f of x equal to the square root of 1 minus x squared. In fact, when n is equal to 5, the terms of the sum are precisely the areas of the rectangles that are shown here, each one having width 1/5 and height equal to the square root of 1 minus I over 5 squared. When n is equal to 10, Our sum gives us the sum of the rectangle areas shown here, and here's the picture for n equal to 20. So in fact, as n goes to infinity, these sums are approaching the integral from 0 to 1 of the square root of 1 minus x squared. The graph of the square root of 1 minus x squared between 0 and 1 is a quarter circle with radius 1 centered at the origin. To see this, notice that the equation y equals the square root of 1 minus x squared becomes y squared equals 1 minus x squared if we square both sides, which can be rearranged to obtain x squared plus y squared equals 1. So the limit of these sums is the integral from 0 to 1 of the square root of 1 minus x squared dx, which is simply 1/4 of the area inside the unit circle, and that's 1/4 pi. Geometric evaluation. As the previous examples have shown, we can often evaluate integrals geometrically. Here we'll use geometric evaluation to arrive at some general formulas. The simplest example is the integral from a to b of the constant function 1, which can also be written simply as the integral from a to b of dx. The graph is simply a horizontal line, so the region bounded by that in the x-axis between x equals a and x equals b is a rectangle with height 1 and width b minus a. Therefore, the value of the integral is b minus a times 1. Moreover, if we have a constant c, the situation is very much the same. The height of the rectangle here is c, and so the integral from a to b of the constant c is equal to c times b minus a. That is, c times the width of the interval. Now let's consider the integral from a to b of the function f of x equals x. Here, the graph is a straight line through the origin. Assuming that a and b are positive, the region of interest lies above the x-axis and is in the shape of a trapezoid. The simplest way to determine the area of a trapezoid is to simply think of the average height of the trapezoid. That would be 1/2 of a plus b here, and express the area of the trapezoid as the area of the rectangle with that height and width b minus a. So we have 1/2 of a plus b times b minus a, and multiplying the two factors together gives us 1/2 of b squared minus a squared. And it turns out that this formula is valid even if a and b are negative, and also if a is negative and b is positive. The integral from 0 to 1 of the square root of 1 minus x squared dx. The graph of y equals the square root of 1 minus x squared is the part of the unit circle in the first quadrant, and so the area under the graph here is just 1/4 of the area of the full circle, and so we get 1/4 pi. More generally, if we have the integral from 0 to r of the square root of r squared minus x squared, then we're dealing with a quarter circle with radius r, and so the integral is 1/4 of pi r squared. The integral from minus 1 to 1 of the square root of 1 minus x squared dx is the area underneath the top half of the unit circle, which will be 1/2 of pi. Likewise, the integral from minus r to r of the square root of r squared minus x squared will be 1/2 of pi r squared. Symmetries. Suppose that f is integrable on a closed interval centered at 0 from minus r to r. Let's suppose that f is an odd function, that is, f of minus x is equal to minus f of x. Then the graph of f is symmetric through the origin. Therefore, the region bounded by the graph and the x-axis has a symmetry which requires that there be equal amounts of area below and above the x-axis between minus r and r. Therefore, the integral from minus r to r of any odd function must equal 0. For example, the integral from minus 2 to 2 of x cubed is 0 because x cubed is an odd function and the interval over which we're integrating is centered at 0. Also, the integral from minus pi over 6 to pi over 6 of sine x dx will be equal to 0 since sine is an odd function. The integral from minus 1 to 1 of x times the square root of 1 minus x squared dx will also equal 0 since we're integrating an odd function over an interval centered at 0. Now let's suppose that f is an even function. Recall that this means that f of minus x is equal to f of x. The graph of an even function is symmetric about the y-axis. So the region bounded by the graph in the x-axis between minus r and r is symmetric about the y-axis. Here we can't be as specific about the value of the integral, but we can say that the integral from minus r to r of f of x dx is equal to 2 times the integral from 0 to r of f of x dx. We'll see later that this is frequently a useful way to simplify calculations. For example, the integral from minus 2 to 2 of x squared dx is the same as 2 times the integral from 0 to 2 of x squared dx. The integral from minus pi over 6 to pi over 6 of cosine x dx, since cosine is an even function, is equal to 2 times the integral from 0 to pi over 6 of cosine x dx. And the integral from minus 1 to 1 of x squared times the square root of 1 minus x squared dx is 2 times the integral from 0 to 1 of that function. Extensions of the definition. If f is integrable on AB, and if g of x is equal to f of x for all but finitely many x in the interval AB, then, by definition, the integral from a to b of g of x dx is equal to the integral from a to b of f of x dx. For example, consider the integral from minus pi to pi of the function sine x over x. This function is undefined at x equals 0, but recall that its limit as x approaches 0 is equal to 1. Here's the graph of the function. It has a removable discontinuity at x equals 0. So it is equal to a continuous function on the interval, except for at x equals 0. So this integral is understood to be the integral over the same interval of the function f of x, where f of x is equal to sine x over x if x isn't 0, but equals 1 if x equals 0. So what we're doing is essentially removing the discontinuity and integrating the resulting function. The integral from a to a of any function is defined to be 0. Note that this is consistent with our notion of the area under the graph, since the area of a line segment should be 0. The integral from b to a of f of x dx is equal to minus the integral from a to b of f of x dx. In other words, if we interchange the endpoints of the interval, then we negate the value of the integral. So, for instance, if we have a non-negative function on the interval a to b, integrating left to right from a to b will produce a positive value equal to the area under the curve. However, if we integrate from right to left from b to a, we'll have a negative number equal to the negative of the area under the curve. The interval additivity property. Consider the function whose graph is shown here. Note that c is a number between a and b. If we calculate the integral of this function from a to c, and then add to that the integral from c to b, we'll have exactly the same thing as if we integrate from a to b. This essentially is the interval additivity property. The integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Now it turns out that the order of the numbers here doesn't matter. In other words, c doesn't need to be the number in the middle. We'll illustrate this with a few more pictures. Consider this situation here where b is between a and c. If we integrate from a to c, and then add to that the integral from c to b, which is a negative number, we'll end up with the same thing as if we integrate from a to b. Here's another picture. Here a is between b and c. Integrating from a to c gives us a positive number. If we then add to that the negative number resulting from integrating from c to b, we will again end up with the same thing as the integral from a to b. And finally here, if a is between c and b, where c is less than b, then integrating from a to c gives us a negative number, and if we add to that the integral from c to b, we'll have the same thing again as if we integrate from a to b. Now let's notice that if we reverse c and b in the second term on the right-hand side of the equation, we have the integral from a to b of f of x dx equaling the integral from a to c of f of x dx minus the integral from b to c of f of x dx. A theorem. If f is bounded and has a finite number of discontinuities, t1 less than t2 and so on less than tk in the interval ab, then f is integrable on ab, and the integral from a to b is equal to the integral from a to t1 plus the integral from t1 to t2 and so on up to the integral from tk to b of f of x dx. Example. Let f of x equal the piecewise defined function that is 1 minus the square root of 1 minus x squared if x is between 0 and 1, x minus 2 if x is between 1 and 2, and 1 if x is greater than 2. Let's find the integral from 0 to 3 of f of x dx. Here's the graph of our function. Notice that the piece of the graph between 0 and 1 is a quarter of the circle with radius 1 centered at the point 0, 1 on the y-axis. Between 1 and 2 we have a straight line with slope 1 crossing the x-axis at 2, and then of course we have the constant y equals 1 between 2 and 3. The integral of our function between 0 and 3 is equal to the integral from 0 to 1 plus the integral from 1 to 2 plus the integral from 2 to 3 of f of x dx. The integral from 0 to 1 of f of x dx is the same as the integral from 0 to 1 of 1 minus the square root of 1 minus x squared, since f of x is equal to that expression for all x between 0 and 1. The integral from 1 to 2 of f of x dx is the integral from 1 to 2 of x minus 2, and the integral from 2 to 3 is the integral from 2 to 3 of 1, or the integral from 2 to 3 of dx. Now we'll evaluate each of these pieces geometrically. The first term is the shaded area underneath the circular arc. The area of the quarter disk shown here is 1/4 pi. That, together with the region we're interested in, comprise the 1 by 1 square, so the area under the graph there between 0 and 1 is 1 minus 1/4 pi. Between 1 and 2, the graph lies underneath the x-axis, and the region formed there is a triangle, and so the integral from 1 to 2 of x minus 2 dx is equal to negative 1/2. The integral from 2 to 3 of dx is just 1 times 1, and so the integral from 0 to 3 of f of x dx is 1 minus 1/4 pi minus 1/2 plus 1 equals 3/2 minus pi over 4, or if you prefer, 6 minus pi divided by 4.